right. All right. So when I left you on Tuesday, we were talking about, again, we were talking about the physical aspects of how we're taking the outside world and converting that through transduction into our senses, into our brains, right? Now we're going to get into the more mind-based. Remember, we talked about the brain versus the mind. Now we're going to move a little bit more into the mind. We're still going to be very physiologically based, but we're going to be talking a lot more about the perception, because these are a little bit harder to explain scientifically. In terms of, we kind of know how neurons work. We know that they build clusters and neural pathways and networks that help us remember things and think about things. But when it comes to thoughts and emotions and how these really play, it's really hard to put our finger on it. So we're going to kind of move to the softer science of things. Now we do, going back to the scientific method, we do measure through observation. So we can kind of see that this is consistent from person to person, how people perceive things. And I'm going to give you lots of examples today with some of those. So again, the difference between perception and sensory or sensation. Sensation is how we take the information in through one of our five senses. What are our five senses? Taste, smell, sight, hearing, and touch, right? Okay, so that's how we get that information in. What do we do with that? Well, that's measured by perception, and it's the method by which sensations are organized and interpreted in our brain. Interpreted. It's a very important word to consider when we're talking about perception. Why? It's what we think. Could it be different for everybody? Absolutely. We might see something. One person might see one shape, and it might mean something different than the next person. So interpretation is really a key word here. So perceptual constancy, these are just our way of being able to kind of develop our own physics in our head. Okay, we're not all born going through physics class, right? We don't enroll in a physics class from day one that we're on this planet, but we know how things work, right? We kind of figure out through learning that if we fall to the ground, it's going to hurt. So we don't mess with gravity anymore. We may not have a term for it, but we know that. We know that the light comes from above, right? These are things that that happen automatically for us. We learn through nature. We learn that something is further away. Like if we have a shape or a figure of a person that's further away, we can kind of guess that because they look a lot smaller, right? Now imagine if you've never seen a person before, and you have one person that's near you and another person just in a picture and another person that's off in the distance. You might consider, again, it might be your interpretation that one figure is smaller than the other. But for the most part, what we learned consistently over time is that these things happen. So size consistency, what we've learned as far as what's relative to our experience, okay? So a chair is generally about the same size, unless you go to one of these resorts where they have those oversized Adirondack chairs, right? Those kind of mess with your mind a little bit. But what do you see when somebody's sitting in one of those chairs? How do they appear? Smaller, right? They appear miniature. So that's size consistency. Shape consistency, again, has to do with what we know, what our experiences are with certain shapes. And brightness, we always assume that light comes from above, right? Because it does. That's what we learned with the sun and moon and other celestial bodies. Now, I'm going to give you some examples of how we can kind of mess with our minds a little bit. Just with I like this lesson because we get to do a lot of visual trickery. Okay, we're gonna, in fact, I'm gonna have one of the things that you're gonna do today is look up some kind of illusion and explain what principles. So kind of pay attention to what we're talking about with some of these. All right, so gestalt principles. Back in the early 20s, there were a group of scientists that in Germany actually that were looking at why people tend to make shapes out of nothing. Okay, it was one of the curiosities that we had, because the couple of the scientists were realizing that people tend to make shapes out of nothing. We kind of perceive things before we actually know what they are. And so these scientists developed gestalt principles. And they're based on the idea that people have a natural tendency to see things, even though they're not necessarily there, okay? So a couple of these principles, and there are about 8 of them. We're just gonna go through some of the most common ones, is figure ground, okay? Again, we kind of know how nature is set up. We've all maybe have walked through the woods and we experience something like this. And by us moving around and touching, we learn that that rock is probably close to us, and that rock is probably hiding that tree, and that gravity is pulling us down, okay? So that's kind of figure ground. We know from top to bottom where things exist and front to back. The other principle that we have is proximity, okay? We tend to clump things together. We look at things as a whole, all right? So if we separated them, what do you see now? Right now you see kind of a cube. You see a 4x4 cube. When we separate them, now we see 4 lines, right? That's a principle of proximity. We also have similarity. So if we were to change any one of these colors, you would group those together automatically, okay? All right, closure. This is one I find the most fascinating in the field of psychology, because it tells me what a person's problem-solving capabilities are. For them to be able to think abstractly, for somebody that might be actually like very literal, they might see like 3 little Pac-Men and 3 little teepees or something. But what else do you see in there? Is there a hidden something? Maybe a star, okay. An upside down triangle, right? Because the principle of closure is looking at the white space, our ability to make something out of nothing. And we actually do this quite a bit in marketing and really in our everyday lives. For example, if I just gave you one of these figures, that probably wouldn't mean anything. But if we rearrange them in a certain way, what does that do? What do you see? Soccer ball, right? There's no circle around there, but we're utilizing our white space, and our mind is automatically creating an image that doesn't actually exist there. How about this? See a cube, a 3-dimensional cube, okay? Is it possible that there's a 3-dimensional cube on that screen right now? Probably not, but using the white space, we can certainly ascertain that there is a figure in there. Principles of continuity. We make sense of the world as we know, because we're well aware how time progresses. We're well aware how lines progress, right? Things tend to flow easy for us. Remember, we as humans are 2 things. What are we? Lazy and prideful, proud, right? And again, lazy I use lovingly because it's just a quick 4-letter word that describes us, but we like things to make sense. So it's easier for us to consider that somebody might have drawn a line through something as opposed to making a jagged line. So for example, what can you assume is happening here? What figure do you see? An X, right? So somebody probably started from the left side of the screen and went down to the bottom of the right side of the screen, right? With those dots. That makes sense to us. That's probably, how many, do any of you see something different, or would you have looked at that and saw something different? Yeah, Sam.
I don't really know what it's called, but what is the thing that go like this? Like that, it has like lines through it. Yeah.
Oh, the DNA. Oh, okay. Okay, well, that's kind of cool. But still, that's continuity, right? Because you're seeing 2 different strands maybe twisting, right? But in either case, we're looking at that as continuous. Whereas, oops, oh, I didn't have the other slide on here. What could possibly be happening here is somebody drew here, stopped here, and then came over here. But our minds automatically tell us that it's probably one continuous line. So that's the principle of continuity. Contiguity, however, is when things make sense chronologically. Okay, so we assume, like, if we see, like, if you walked in here today and there was a plant here, and you probably don't know much about me, I don't like plants, but your assumption would be it wasn't here the last time I was here. What would your assumption be? Or likely I brought it in, right? That would be your automatic assumption, because it wasn't here before. I was here before, but that plant wasn't before. So you might assume that one event led to the other, okay, based on whatever you know about me. I'm terrible with plants. So anybody that knows me knows that I would probably not bring a live plant in here. So common region. I didn't have a clever little slide here, but common region is just the grouping of different symbols, different figures that might have meaning for us. And again, here's contiguity. This is a better description. So instead of going from A to B and C to D, perhaps A to D could have occurred, C to B has occurred, but we automatically assume that A goes to B and C goes to D. Okay. And again, another example of closure. All right. So one of the things I like to use, especially in modern day terms, and any graphic artists here? Anybody going into art or anything? Okay. So this would probably apply to you, just some of the principles that we use, because when we're grouping things together, we're making presentations, we tend to do what? We want to be organized, right? We want people to make sense of things. So I got this off of BBC News, just as an example, because I was looking over it and I said, well, that's kind of cool how everything is grouped together. Okay, so for example, we have on the left side, we have our menu, which really shows proximity and similarity. They're all in blue. They're all stacked on top of each other. You can see they're kind of justified right. And there's a clear definition between this side of the page and the other side of the page. So we know automatically that this is probably, if we click something here, it's going to take us to a different page or a different category or something, right? Continuation. Even though, we see these little reports here, what's different between this report and these reports? What'd you say? They're grayed out, okay? So what can you probably assume based on this gray line? Importance, right? Okay, because we have like a Q&A, case for war, we have Dr. Seuss, we have streaming ahead, but up here we have a couple more important, like your main topics up here. And then this is kind of a divider to tell us that there's something a little bit different, right? So this is an example of continuation. And then of course, similarity down here, okay? We have things grouped up based on section, okay? So if we were interested in what's going on in the world in the Asian Pacific, or for whatever reason, we know that we can go here and probably go to a subcategory. So anyway, that's just a kind of a graphic example that I like to use with that. All right, depth perception. I think we touched upon this on Tuesday. So depth perception is using more of our senses to really determine how far something out is from us or how close it is. So if we have monocular depth, monocular vision, like we only have one eye, what are we lacking? Other than depth, yeah.
The ability to determine the range.
Right. Because we really need both eyes to help us determine how far something is, or if it's moving closer to us or moving further away. So that refers to, so monocular vision is just using one or half of your vision, like one eye or the other. And that could be for many reasons. Maybe somebody has lost capability in their eyes, or maybe they had an injury and they had their eye covered or something, right? But that takes away from your ability to perceive depth in that third dimension sometimes. Binocular obviously is two, using two eyes to do that. But when we're talking about monocular vision, oh my gosh, what is that thing? Oh, cricket. Is he bothering anybody? Anybody want me to get rid of that? Yeah, yeah. Yeah. No, no, no. Go that way. Come on. All right, you got him. Thank you. Don't eat it. So when we're looking at binocular cues, we're looking at things like interposition, linear perspective, all these things, which I'll kind of go over one by one. So monocular, again, one eye. That means that we're not necessarily using two eyes to really determine anything. We're using just, this is just our ability with one eye. So interposition is the position, like we know, we've learned that big objects close up might overshadow other objects. So in this example, what can we say about the tree in relative position to that rock?
It could be right or left.
Well, it's behind it,
Yeah, it's behind.
right? It's behind it. Well, that's what we're assuming. Now, we don't know. Maybe this is one of these new generation pet rocks that starts growing trees, right? That could be an alternate explanation. But for the most part, what we learned about our rudimentary physics is that tree is probably behind that rock and that rock is in front of that tree, blocking the view, right? That's interposition. Linear perspective. We know without having a picture, let's see if it gives me another example here. Nope, it doesn't. Let's see here. So we know without having any other cues, I mean, that might just look like a triangle to you, right? By connecting the ends right here. So what if I started, I'm a horrible artist, I apologize. So now what can we assume about that tip of the triangle? We just created a three-dimensional figure, didn't we? Okay. Just because we know the relative size of a person has changed, and we also know that things tend to fade off in the distance. So that's the example for linear perspective. Okay. Relative size, again, this is just this helps to solidify this. We know the average size of a person. If it's smaller in the distance, we can assume based on size what or how close or how far they are away from us. Texture gradient. We also know, just based on our experience, that we get more details, we get more texture when we're what? Close or far? Close, right? Things tend to fade. Like these are probably the same rocks back here, but you can't see the details like you can off in the distance there. Okay. Aerial perspective. For those of you that are artists, if you are going into the art field or do it amateur or whatever, we know that off in the distance again, we have our texture gradient here, which diminishes the further back you go. But what else do you have back here? Haze, right? So haze and clouds and stuff. So that kind of indicates to us, based on our experience, that those mountains are off in the distance. And then motion parallax is another principle that we can look at. I don't know, is that showing? So we know that when we're moving at a fast pace, like maybe looking out the window of your car or the window of your bus or whatever, wherever you're at, what tends to move slower in your field of vision? Things that are, what's that? Things far away, right? They tend to stay relatively consistent than something that might be next to you or closer to you. That's going to go across your field of vision a little quicker. Okay. All right. So I like to, I have a couple examples here of, let me turn off the lights so you can see this a little bit better. All right. So I have up here labeled I don't know how to do this any better. This is not a great. Okay, so I have up here, can you all see that all right? So I have up here labeled tiles A, B, and C. Which one is brighter than the other? You say B? Show of hands, how many think A is brighter of the three? How many of you say B is brighter than the three? How many of you say C is brighter than the three? Okay, no. Oh, you got C? Got to take her for C? Just to be different, right? Okay, so this is a demonstration of brightness constancy. Okay, so we know that light comes from where? In this picture, where do you think light is coming from? Top right. Okay, up here probably. So how do we know that? Why do we think that? Because we have a shadow going down to the bottom left. So our assumption is that light is coming from there. So what does that tell us about tile B? That it's in the shadow, right? So we would assume that it's brighter. But this is what our brains automatically do for us. It's the same color, right? Same shade. So that's brightness constancy. That's telling us that light is coming from somewhere else. So therefore, this tile must be a different color, okay? Let's try another one. How many of you think A is darker than B? Oh, you're catching on, aren't you? Okay. Brightness constancy. Where do we assume that light is coming from? From behind, right? From top left, shining down. Okay. But in reality, just based and we kind of have shadows in here, but in reality, they're the exact same color. I didn't alter any of this. I just blocked out the contextual cues that we had there. So isn't that wild? It still looks, you put the context back there, it looks a little bit different. It looks like it's bright white. See it again? All right, so that's just an example of how physics, how our understanding of the world around us really plays into what we see and how we view it. Okay. All right. All right, so let's talk about binocular depth and cues, because really what you were doing there in that last picture, you're trying to use both eyes to really build a picture, when in reality, it was just really one. It was one dimensional. It was a flat dimension. We were trying to force it to be three-dimensional, but it wasn't. So with binocular depth, what we have two principles here: is convergence and binocular disparity. And I think your book covers both of these, and I'll explain what these are. So convergence is actually using the muscle in our eyes. So if you were to put your finger in front of you and try and focus on the tip of your finger, what do you notice with your eyes? What are your eyes doing? They're starting to cross, right? So your brain, remember the left and right visual cortex, your brain is telling you that your eye is actually moving. So it's telling you relative what position your finger is in front of your face. Now you move that a little further over, a little further away from you, and further away from you, you have a little bit of a harder time. Your brain can't really determine which eye is moving or which eye isn't. However, like I'm looking at my camera over there, looking at my phone, I can tell just by looking at it, just relatively, that it's three-dimensional. Okay, and I can tell approximately how far that is. That has nothing to do with convergence, because my eyes aren't really converging on that point. What I am able to see is slight differences between what my left eye is seeing and what my right eye is seeing. How many of you have ever gone to like a 3D movie? Okay. Or do any of you have the VR, virtual reality headsets? Okay. What do those do? How do those work? Okay. Okay. How about three-dimensional cameras? Like if you've seen a 3D movie, how do those work? Have you ever tried to take your glasses off and watch a three-dimensional movie? What happens? It's blurry. You can't see it, right? So what those glasses are doing and what the virtual reality headset is doing is it's tricking your eye and it's giving you two images as they would appear as if you had two eyeballs looking at that camera over there. Okay. So it's telling you that there are two images, and even though your eyes aren't moving, your eyes aren't really doing any work at all, but it's giving you two images and it's telling you that this is a three-dimensional item or a three-dimensional object off in the distance. And it moves as your eyes would. So your eyes are really that sensitive that they can pick up on very small depth cues and give you relative position. Okay. This would be an example of like false depth perception. Okay. We know that this is probably not a three-dimensional object here, or tunnel, or whatever you want to call this. But based on what we know and how we've experienced things, we can tell just with those rectangles how it's forming. It's given us a three-dimensional view. Okay. This was best demonstrated. How many of you have heard the visual cliff experiment? So anybody that deals with kids knows what they make mistakes how many times? A lot. Okay. There are certain things that they don't do very many times, like touch a hot oven, right? Or fall off the couch, right? Because earlier on, very early in you're right around 6, 8, 9, 10 months before a year old, they're able to ascertain, they're able to determine what visual cues can lead them into danger. Okay, and they demonstrated this back in the 60s through the visual cliff experiment, where they had a baby stand up on a ledge, and even though there was glass covering it, it still had the perception that it was a drop and that baby would not go across that cliff, because that child knew. Okay, children know earlier on what could lead them to danger. So something like that they might try to crawl through or something, because that that gives them the perception that there might be some place to go if they felt safe to do that. All right, another perceptual illusion, or perceptual illusion that we have is the Muller-Lyer illusion. Many of you may have seen this before, but our perception is that the bigger something is, the longer that line might be, right? So looking at this, how many of you would say line A is longer than the rest? By show of hands. How about line B? Okay, got one. Got a couple of you think line B is longer. How about line C? Think line C is longer? Okay. What do you think? What? Right. If we measured these, if we took the visual cues away, we would see that those lines are the exact same size. Okay. Yeah. Uh-huh. Right. But the question was which line is longer? So the arrows, the visual cues are the arrows. The visual cues are telling us that this one seems a little bit longer. Like if you look at that line, does it look longer than that one without those cues? Yeah. So if we measure them end to end, just from the end point of this line to the end point of that line, discounting the arrows, they would all be the same. Okay. That's the Muller-Lyer illusion. Illusions of motion. We have a couple principles here that that give us the illusion that things are moving even when they're not. Okay. So I don't know if any of you can. Does that look like it's moving to anybody? Yeah. Okay. Okay. So what's happening here is this is both. This is both a sensory overload and it's a cognitive overload. So we know that there really aren't any contexts. There aren't any visual cues to tell us that there, other than the blue and yellow, there really isn't much context to describe and tell us that these things are stationary. Okay. Each one of these are off by just a little bit, enough to make us think that this is moving in one direction or another. Okay, what direction is this moving for you? Clockwise, counterclockwise? Counterclockwise, okay. I actually can't see that because I'm not in front of it. Okay, it looks a little bit. How about this one? Right. It's actually not moving. There's nothing moving on there. Yeah. Okay, that is not a GIF or whatever. But what's happening is the difference between the light and the dark. There's no contextual clues. So what we're assuming just by moving our eyes is that something might be moving as we're moving our eyes around. So if you look perfectly still at one center point, it's less likely going to stop moving. But if you look around to different things, to different areas, it's going to look like it's moving. Pretty cool, right?
So how do artists know that this will work?
Because we're well aware of how perception works. Yeah, yeah. It's scientific. I mean, we know that we know that going. For example, if you had a small light in a dark room, you might think that light is moving around because you don't have any other contextual clues to assume that it's not doing anything. Like if we had like lines down the middle, that would probably stop these things from looking like they're moving because now we have contextual clues. But with nothing else to really tell us that there's no motion in here, we're just going to assume that maybe there's some motion because our eyes are moving and it's moving those colors ever so slightly. Okay. All right. Another, and this is kind of an important concept with, and we're going to definitely come back to bottom up and top down processing. So bottom up processing and top down processing, it's our way of kind of gathering evidence for maybe a thought or an experience that we're trying to investigate. So for example, you're driving around maybe right outside highway, what is it, Highway 5 that gets out of here? So heading out Highway 5 and you see two little glowy dots in the distance. You're driving at night. What does your mind tell you? It's a deer. Why? Okay. Okay. What? So why does our mind why does our mind automatically go there to hitting a deer or a deer in the distance? We maybe have seen that before, right? We've heard about that. We're kind of fearful of hitting a deer, aren't we? So we automatically, build that thought in our head. So we are using top-down processing because we see evidence of something in the distance, and our experience tells us that little glowy lights in the middle of the night could be harmful for us. So we start building this story. How many of you live in like an old house that you hear something creak at night? Okay. What does that do to you sometimes? You build a story in your head automatically, right? You think it might be a ghost or an animal or a person or whatever. And we use that as just as self-protection and survival instincts that kick in there. We do this to build a story so that we can better protect ourselves. Bottom-up processing, a little bit different. So now we're kind of becoming little investigators when we're using bottom-up processing. We may not have a clue what's going on. Say you've never seen a deer. Maybe you're from, I don't know, what place doesn't have deer? Huh? How about Florida? Anybody from Florida? Okay. Do they have a lot of deer in Florida? No, no deer in Florida. Are you fearful of deer crossing the road? No, no, because you haven't seen that. You haven't experienced that. You probably haven't talked to many people that has happened to. So so Mark is driving off on Highway 5 in the middle of the night, and he sees two little beady little eyes or something glowing off in the distance. Mark might say, "Huh, I wonder what that is." Not building that, not using that top-down processing because he hasn't had that experience yet. So as he gets a little bit closer, he might be slowing down to investigate and sees, maybe in his headlights, sees a little figure or something. So now we have eyes and we have a figure, and he's still, I wonder what that is. And he's slowing down and maybe looks off to just verify, gets a spot beam out or whatever he's got, or a flashlight, to see what's off in the distance. And so that's using bottom-up processing. That's when we don't have a context to pull from, and we're just gathering evidence to build a bit bigger picture. Okay, and that helps to develop our perceptual sets. Any questions on top down? We're going to see this again, so we're going to be using this again. All right. So with perception, we get preyed upon a lot. Okay, we do. We get preyed upon a lot in media. We get preyed upon a lot in advertisement. One of the cool areas is magic, right? Magicians frequently use illusions to trick us to think that we're seeing something that we're actually not. And they may use either sleight of hand, having you watch something out here while the other hand is doing something, or their partner is doing something, right? They may use something like strings or wires or something that they know that you can't see because your focus is elsewhere. Okay, so they use a bunch of these principles to, because Hunter, I think you asked, how do artists know? And it's because they may have practiced this over time, or they stumbled upon some principle that tells them that, hey, maybe if we create this illusion, we're going to trick somebody, and it's going to be kind of cool, right? All right. So what I would like to do, this is kind of cool. We'll do this. How much time we got? I want to do one activity before we leave here today. So what I'd like you to do, this is going to give you a flashing picture. And your task on the following slide, you'll be shown two images flashing alternatively. The images are identical except for one major change. See if you can spot the change before time runs out, and then try this again with another set of images. All right. So you ready? Okay. Hold that. Hold it. Don't blurt it out yet. All right. How many of you got it? How many of you didn't quite see the change? Okay. One more time. How many of you did get it? Okay. A majority of you. Okay. So what was the change? What was the difference? The horse, right? The horse. Now, what would happen? So it took a little bit longer for you to get that, right? Now, what would happen if we were looking at that picture and the horse just disappeared? We probably would have had that in a split second, but we were flooded with white space. So that kind of overwhelmed our senses a little bit. And it took us a while to be able to figure out what was appearing and reappearing, or disappearing and reappearing. So let's try one more just for the fun of it. Raise your hand when you think you got it. Okay, how many of you got it? Didn't get it? What was it? The tower. It was the tower. Here, let's see it again. That one. It's a little bit more complex because we had a lot of similarity in there, right? But your senses are being flooded. Your perception is being flooded with the bright white space. Now, again, if that disappeared, we would have you would probably notice that a little quicker. All right. So what I would like to do is break you off into groups today. And if somebody has a computer or something, I want you to go out and seek out an illusion. Okay, a visual illusion, perceptual illusion, whatever you can find out on the internet, or maybe you have one in mind that you've used before. and explain in like one or two principles that we talked about today. It could be gestalt. It could be linear perspective or something like that, or linear perception. Use one of those principles that we talked about today to explain what you found. So let's do groups of 3 and 4 again. So the 3 in the back there, U4, U3. The 4 of you in the back, and then the 3 of you. Does that work? All right.